Hello to everybody. I'm very glad to introduce Bob Frank, Chair and Professor of Linguistics at Yale University. He received his PhD from the University of Pennsylvania in the Department of Computer and Information Science. After that, he joined the Department of Linguistics at the University of Delaware, and later the Department of Cognitive Science at Johns Hopkins University. Since 2008, he's working in the linguistics department at Yale University. He's also affiliated with Yale's program in cognitive science and the CLAY lab, that is the computational linguistics at Yale lab. Bob Frank is interested in applying insights from computational modeling and mathematical formalization to uses in theoretical linguistics, especially syntax, language acquisition, and processing. For example, he has worked extensively on the application of the Tree Adjoining Grammar formalism in syntactic theory. And he has also explored the application of such methods to problems in natural language processing. So let's welcome Bob Frank, who is going to give us a tutorial on the formal complexity of natural language grammars, revisited perspectives from neural networks.
So thank you very much, Leo. I would thank you very much for the really generous introduction. One correction is, thankfully, I am no longer chair of linguistics. So actually, that's the reason I'm able to get anything done. But thank you very much. So let me share my screen. Hang on just a second. Okay. So can you guys see that? That's good. All right. So what I was just looking at the distinguished group of scholars who are out there in the ether, and what I'm going to say, a lot of what I'm going to say, I think is going to be very old hat to all of you. Many of you are far more expert in much of this material than I am. But what I'm going to try to do is give you what I think is this kind of perspective that linguists take on this, or that linguists, if they had a certain level of mathematical sophistication, might take this, because I think a lot of linguists find some of the grammar induction and formal grammar work a little bit daunting. But I want to see, at least kind of give you my perspective on what I think this discourse is between, on the one hand, the formal grammar community and the grammar induction community and the linguistics community, and the kind of concerns that community has. So let's start, maybe not at the beginning of modern linguistics, but the early days of modern linguistics in Chomsky's aspects of the theory of syntax. So Chomsky lays out what he characterizes as two criteria for what we want out of a linguistic theory. So the baseline criterion, I should also say that if anyone has any questions, by all means, please feel free to interrupt. And I'm happy to have this as a conversation rather than just me going on for however long I go on. So I don't know how exactly the best way to do that is, because I'm not sure that I will be able to see all of the things. But just talk up, just raise your voice and say, hey, I've got a question. Okay, so anyway, going back to Chomsky in 1965, the initial criterion that Chomsky imposes is what he calls descriptive adequacy. So the idea is that what a linguistic theory is going to be is some kind of class of grammars. It's going to characterize, give you some meta language to write, in which we could write down descriptions of individual languages. So the question of descriptive adequacy is that theory, is this meta language sufficiently powerful to provide descriptions of the individual natural languages that we see? So can we characterize the generalizations that we find? So in a certain sense, this is a kind of lower bound on complexity, right? That our theory has to be sufficiently expressive to capture the kinds of things that we want to capture. Okay, and so, and then Chomsky did this exploration, actually did it earlier than 1965, did it in the late 50s, where he characterized a range of types of formal devices. And he said, and then he started saying, okay, well, let's see if the formal devices are sufficiently powerful. The Chomsky hierarchy, as I'm sure you all know, there were these, it was characterized, interestingly, both by kinds of grammars and kinds of abstract computational devices, automata. So it went from the finite state, which was characterized as deterministic or non-deterministic finite automata, or right or left linear grammars, to the context-free grammars or push-down automata, to context-sensitive grammars or linear bounded automata, and finally unrestricted grammars or Turing machines. Okay, so I had this hierarchy of inclusion of sort of power of computational devices, and he proceeded to look at, well, what are the, if we're looking for a lower bound, what is the least expressive computational class that can characterize natural language? All right, so the first observation that Chomsky made in, I think, the mid-50s was that this finite state was not sufficiently powerful. And the thing that he was responding to was, I think, work in behaviorism in psychology in the 50s, which was kind of a dominant model of linguistic behavior. And the idea was that each subsequent word or linguistic behavior would be conditioned on the immediately prior one. So essentially a first order Markov chain. And Chomsky points out that that kind of thing is insufficiently powerful because language shows certain kinds of dependencies that have this unbounded character. So he showed examples like this kind of center embedded sentences. This is an example that I invented in a rare moment of procrastination years ago. But it's an example of, where we've got this triply center embedded dependency. The book, an Italian I never heard of, wrote, got published. And we see that there's this dependency between verbs and their corresponding subjects. And that dependency can range over some kind of unbounded distance, and we get nesting. And Chomsky demonstrates that this is the kind of dependency, at least generalized, that cannot be characterized with finite state means. Okay, I'm sure this is familiar to everybody. All right, so then he says, okay, well, what about the next thing? What about context-free? And giving a kind of lower bound argument of this sort, Chomsky actually didn't do that, right? His argument against context-free grammars, as we'll see, had nothing to do with kind of descriptive adequacy question. But it turns out Stuart Schieber, some 30 years later, did provide such an argument where so the story goes, I've never asked Stuart about this question, but the perhaps apocryphal story was that Stuart was skiing in the Alps and had this epiphany that the German spoken in Switzerland actually provided the crucial bit of evidence for this kind of lower bound complexity. So the point is that in the variety of German spoken in Switzerland, to say a sentence like, we let the children help Hans paint the house, the word order is something like the example that's given there. It's something like, we, the children, Hans, the house, let help paint. And so the point is, we see this kind of crossing dependency order, that there's a kind of the ordering of children and let, Hans and help, and paint in the house. This is the relationship between a verb and its corresponding object. And so we see that this is a kind of crossing order. It's not nesting the way we saw in the previous example. It's kind of crossing. We see blue, then red, then green in the nouns, and then blue, and then red, and then green in the verbs. And the point is that this is a kind of pattern that is not expressible in context-free grammars. Now, it had been observed prior to Schieber that this kind of word order exists in Dutch. So it had already been observed that if you want to characterize that dependency structurally, that was beyond the power of context-free grammars. But unlike Swiss German, Dutch does not show case marking. So there's no kind of explicit marking in the surface string about the relationship between the verbs and the nouns. And the crucial bit, and Schieber's observation about the Swiss German, was that the nouns in Swiss German show this case marking. So in a certain sense, this kind of cross-serial dependency is visible on the surface in the surface string. All right. Okay, so that's again, lower bound in terms of complexity with respect to descriptive adequacy tells us that context-free grammars are insufficiently powerful for characterizing natural language syntax. All right. So then we'll ask, what did Chomsky do next? What he actually, let me go back for a second. What he actually did was he then said, well, we should go up to another formalism. And he had skipped context-free for another reason that we'll see in a moment. But he jumped up to another formalism that, as we'll see, is quite powerful indeed. And one thing that's interesting is, as you all know, no doubt, the gap between the expressive power of the context-free and the next higher class, the context-sensitive, is substantial indeed. So this gulf, even though it doesn't look very large, is quite large in terms of what can be expressed. So in a certain sense, it kind of, the kind of using formal constraint to understand the expressive limits of natural language grammar kind of runs out of steam to a certain degree at this point. All right, now the second criterion that Chomsky imposed was what he called explanatory adequacy. Okay, so explanatory adequacy is a term that is thrown around, and Chomsky uses this term in a somewhat idiosyncratic sense. So I think it's worth reviewing exactly what he says. So the question I think he was concerned about was, well, does our linguistic theory, or does what we attribute the knowledge that a child has going into the process of language learning, does it provide an account of how that child will go from some finite sample of data into a grammar? Okay, so how do you project from data, what Chomsky calls the primary linguistic data, into their abstract representation of grammar in such a way that it is going to match the kind of grammars that we see in adults who speak that language? And Chomsky's idea was that, well, in many cases, of course, there's going to be lots of ambiguity. The evidence will underdetermine what the right grammar for a language will be. And so Chomsky's idea, which essentially is the idea of inductive bias, perhaps not surprising, he had worked with Nelson Goodman when he was an undergraduate and graduate student. The idea is that the theory is going to provide a kind of ranking of grammatical hypotheses, what Chomsky formulated as an evaluation metric. And this is going to determine what is given a bunch of grammars that are compatible with some finite set of data, this ranking or evaluation metric is going to say, okay, all these are compatible, but this one is better than this one is better than this one. Okay, so even if I've got multiple, if there's grammatical ambiguity with respect to one grammar or the other, the idea is that what the grammatical theory provides is a way of assessing distinctions between these. And the intuition behind the ranking was often a kind of simplicity metric, but as Chomsky rightly points out, one needs to put a little bit of meat on the bone of a simplicity metric by itself. That doesn't define it. It's really going to be how does the grammar work itself? What is its mechanism? All right, so let me give you an example of that kind of simplicity metric. Okay, so here's the kind of canonical example that gets discussed in the literature, and I'm sure you've seen it, but let's just review. And so this occurs in the kind of child learning English, learning how to form questions. Okay, so you see that you have a sentence like the zebra is resting. You want to form a question. The corresponding question in English is the zebra resting? Okay. You hear a sentence, this is like, the zebra is hoping that the lion has eaten. It doesn't want to get eaten itself. And the child will hear corresponding question, is the zebra hoping that the lion has eaten? Okay. Now the question is, what is the right characterization of formation of questions in English? Well, it has something to do with moving an auxiliary like is to the front of the sentence. So you get, is the zebra resting? Now you see these other kind of examples, somewhat more complexity, because now there are multiple auxiliaries. There's the green auxiliary is, and there's the red auxiliary has. And what we want is that the green auxiliary is the one that will be fronted to form a question. So we get, is the zebra hoping that the lion has eaten? And not the red one. We don't want to say, has the zebra is hoping that the lion eaten? Quite that, okay? So how can we characterize that? Well, imagine you have a grammar formalism, and it's going to allow you to express some way of mapping between the declarative and the interrogative, assuming that's something the child has to learn. the correspondence between these two sentence types. And Chomsky points out that there are at least two ways of doing this. Way one, you could imagine a grammar would say is, well, move the first auxiliary. Okay, so just scan the string from left to right and find the linearly first auxiliary and move that to the front. And in these sentences, you scan, you'll get this one. Well, there's only one here, get the right thing. This one, you'll scan from left to right, get this one, move to the front, does correctly. So green for good, right? Okay, second hypothesis, move the main auxiliary, okay? And this is not so we're not going to take the linearly first, we're going to take the syntactic structure, and we're going to assign some syntactic structure, and we have to define exactly what we mean by main, but something like closer, the path between it and the root is shorter than the other. Okay, so, and we see that that will define also this green auxiliary. Okay, so we have two hypotheses, a linear rule and a structural rule. And if this is the data that children see, the data is ambiguous between these two rules. And so these hypotheses are, there's quite an unfortunate typo here. These hypotheses are actually, actually, no, there's not a typo. These hypotheses are, in fact, it's typically assumed, perhaps plausibly, that examples of the sort that would disambiguate those hypotheses are not part of a child's experience. So the examples that would distinguish them are going to be examples of the following sort. These are examples where we've got an auxiliary verb that is linearly first, but is not the main auxiliary. And these are going to involve typically things like relative clauses modifying the subject, or sentence initial adverbial clauses. Okay. Now it turns out that these kinds of things are, if we look in corpora of even adult speech, but certainly in child-directed speech, they're exceedingly rare. And so the point is that these examples, if the zebra that is resting has eaten a bug, if we were to apply the move first, that would define this is, and we'd get this is the zebra that resting has eaten a bug, the wrong answer. And if we apply the main, move the main one, we get the correct answer, has the zebra that's resting eaten a bug. All right, this is all familiar. Now, the idea that we want is so there are two paths you can take. And I think this is where there's some disagreement or sort of misunderstanding of Chomsky's game. I think one game could be that we want, therefore, a formal system that simply does not permit the statement of a rule like move first. That's one possibility. That's simply not a possible grammatical rule. And so therefore, the reason why the child converges, say, to move main is because that is the only thing that is accessible to them. The way that I think Chomsky was thinking about it, at least in 1965, was rather that that's not necessarily the case. What we need instead is that even if the grammar formalism allows us to express both such rules, both such grammars, it could be that one is harder to say and the other one is less hard to say. And so if the statement of the rule for move main is simpler than the statement of the rule for move first, then that would be a good answer to this question of explanatory adequacy. Essentially, we've got an evaluation metric that prefers what we want as the quote unquote right answer. Now, of course, on the basis of the data in the abstract, from the perspective of the Martian scientist, there's no right answer per se. What we mean by right answer is simply, what do children do, right? There's a kind of ambiguity that's present in the data that it does not uniquely determine it. And so in a certain sense, we're not requiring that, the requirement is not that the child converge in the face of unambiguous data. It's rather that the child prefer one hypothesis in the face of certain kinds of data. All right, that was the game. Now, let me just say one more thing. And so that is to say that you could imagine in Chomsky's view, at least this version of Chomsky's view, that if a child were presented with data from this language that makes use of the move first rule, that data would then be unambiguous in favor of a rule that involves linear generalization. And so the expectation was that the child could learn that in principle. Maybe it would be more difficult in the sense that the grammar would be more complex. But the claim is not that the child could not, in principle, learn such a grammar, but rather that given ambiguity between that hypothesis and the other one, the child is going to prefer the structural rule. All right, is that clear? All right, good. Now, so what does this all mean with respect to the Chomsky hierarchy? Well, Chomsky actually used this kind of explanatory adequacy argument to argue against context-free grammars. So he was looking at things like, well, he was looking at different kinds of phenomena, but here's a kind of phenomenon we can imagine. Here's a case of instance of reflexive pronouns in English. And as you know, reflexive pronouns in English are inflected for gender. So we have sentences like Fred admired himself and Alice admired herself. And the point is that if we have syntactic structures that correspond to those sentences, that's fine. And we could write down a context-free grammar that generates such sentences. And the point is that that grammar, if we allow noun phrases to be generated like Fred and Alice, and now other noun phrases to be generated as himself and herself, such a grammar does not constrain the gender relationship between, on the one hand, the subject and the gender of the object. Okay, and that's not to say that one can't do it in a context-free grammar. Okay, one can do it. So you can write context-free grammar rules which explicitly encode the gender of the subject, and you can constrain the gender of the subject to match the gender of the object. Okay, so it's certainly a doable thing. But Chomsky's point was that if the child is presented with data that does not drive them towards such a grammar, but by default, they wouldn't necessarily prefer such a grammar. So to the degree that the data is ambiguous between the grammar with gender and the grammar without gender, children will prefer the grammar without gender. And yet we see phenomena that suggest that they do need to coordinate subjects and objects, the gender of subjects and objects in cases of this sort. Okay, that's the idea. Now, of course, that is assuming that the data are actually ambiguous in this way, and of course they're not, because children do see examples of this sort. But the logic is the same as what we saw before. The formalism allows us to express both the gendered version of English and the non-gendered version of English. The formalism sort of makes it simpler to say one as opposed to the other, and yet we see that, in fact, what we have is something that requires this kind of mechanics of feature passing. All right, and so on that, for that reason, Chomsky then made the argument, I think kind of argument of explanatory adequacy, that this is not making the right thing simple. We would like to see that the grammar makes simple the kinds of generalizations that actually occur in language. All right, okay, so so what corresponds to simple in a context-free grammar does not correspond to grammatically natural. All right, so what Chomsky then proposes, this is what the sort of final conclusion in syntactic structures, was essentially this view of transformational grammars. And so remember, a transformational grammar is a context-free grammar base plus some set of rules that essentially take these trees and munge them in some structure-dependent, well, what appears to be a structure-dependent way. And Chomsky's claim is this provides a natural account of grammatical phenomena in the sense that non-structural generalizations are at least harder to state. Not that they're impossible, but that the generalizations that are sensitive to structure are the ones that are simpler to state. So on the line of the evaluation metric, that's what we want. So, you know, if we think about reflexivization, we get the simple rules, and then we get some kind of reflexivization transformation that independently of the phrase structure rules is going to take care of the relationship between the subject and the object. That's the game. That's the idea. Now, that's the view that Chomsky took, and this view about, you know, relative complexity of different ways of characterizing a generalization. Now, let's compare that to a different view of explanatory adequacy. And I think it's the view that is much more prevalent in this community and the community that thinks about grammatical complexity or formal complexity. And that's, I think, a view that comes from Wilhelm von Humboldt. And so the idea is not that what we want from a grammatical theory is an evaluation metric. What we want from a grammatical theory is a kind of upper bound on complexity. We want that the grammatical theory should limit the possible hypotheses to those that are compatible with the patterns that we see in languages, with linguistic universals. So the descriptive adequacy kind of imposed a lower bound on complexity. It's got to be sufficiently powerful to state what you want to state. And von Humboldt says, but no more. Okay, you don't want extra. You know, in a certain sense, one can see Chomsky's earlier inquiry into let's look at increasingly powerful classes of grammars as an instantiation of this idea. But I think at the end of the day, what he was actually driving for wasn't that. It was kind of, I think, looking back on it, I don't completely understand what the agenda was, but maybe there was no single agenda. So this is von Humboldt's idea. And the idea with respect to how does this relate to explanatory adequacy? Well, the idea is that, well, if a grammatical theory limits the hypotheses, simply doesn't let things, let's say, linear generalizations like move the linear leaf first auxiliary to the front of the sentence, it simply makes those impossible to say, then the data are no longer ambiguous. Okay, and that should, could, does make grammar learning easier. Okay, so you simply do not entertain that in a certain sense, the problem of projecting from a finite sample of data into grammar is easier because the hypothesis is that the data are no longer ambiguous because the range of descriptions of the data are more limited. Okay, that's the picture. Okay, now, if we think from that perspective, then Chomsky's claim on transformational grammars is problematic indeed, because as you all know, in the 1970s, Peters and Ritchie proved, I was very proud of myself to have found this week a picture of Bob Ritchie, whom I had never seen, but sadly, we should pay tribute to Bob Ritchie, who passed away a couple of years ago. So there is now a picture of him up on the website of the University of Washington, where he was chair of the computer science department for some years there. Anyway, they proved that transformational grammars are very powerful indeed. Indeed, they exhaust the recursively in languages. So what that tells us immediately, first of all, is that Chomsky's claim about transformational grammars, even if it's true that it makes the structural things simpler, it can't be right that it cannot state linear generalizations, because if they're Turing machines, they can state anything, at least anything that's computable. Okay, so in that sense, they don't limit the expected range of analytical options, right? They don't satisfy von Humboldt's desideratum of constraining possible grammars to only those things that we witness. So in fact, there was a bit of a turn in linguistic theory from the original evaluation metric view to the von Humboldt limit what the possible grammatical hypotheses are view. I think my guess is sometime in the, I don't know, 70s. Let me guess, I wasn't around yet. But certainly when I started learning linguistics, I think that was the kind of accepted view of what the goal of a grammar was. And so then the question is, well, what are these constraints? How do we impose limits on grammars? And you guys have studied introductory linguistics or even not so introductory linguistics, and you've seen that work in generative grammar that tries to do these things essentially stipulates properties of grammars. So I've picked some examples of things that are kind of relatively formal in the sense that they're not saying about substantive combinations of certain features. They're kind of constraints on the structure or constraints on operations that, you know, are interesting, and people have shown in the literature that they do a certain amount of work. So the final over final condition, those structures where a head initial phrase is contained in a head final phrase in the same extended projection domain. Now, interesting. I don't know why that would be true, but interesting, and people have shown that that has certain kinds of interesting consequences, okay, and the like. All right, so we're gonna just stipulate this, and that's satisfying to a certain degree, but if you are of a computational or mathematical sort, you might find this somewhat unsatisfying. The big question is why? And the alternative is well, why don't we think about going back to what we said before, this from Humboldt perspective, derive constraints on what's possible from this kind of exploration of the formal properties of grammar. Okay, so this is, I think, this is all a long lead-in to, I think, what the community of people who do formal complexity of grammar, where it comes from. It's not as direct as I sometimes think about it, that I think, oh yes, Chomsky in syntactic structures laid out, you know, let's just explore the Chomsky hierarchy, and he started this thing and he got bored. But I don't think that's, I think it's actually quite a different perspective that leads to this. Now, it's also interesting if you looked at so Chomsky's own intellectual history here. He actually changed his perspective on this. So in the 1980s, after he had kind of gotten bored and when he was convinced that transformational grammar was the right thing, and then it was pointed out that transformational grammar was quite powerful, he said something in an interview. He said, well, we're now asking whether there is some reason of principle why these grammars, that is to say, are possible human grammars, must generate recursive sets as opposed to, say, arbitrary RE sets. So do they even have to be computable, right? Decidable. And he says no serious argument has ever been advanced in support of such a claim. Okay, so even the idea that the grammars need to be recursive, why should we think that? No reason to believe that. So that's 1980, 41 years ago. God, time flies. All right, and what was interesting though to me was that if you looked 25 years later, Chomsky had evidently changed his mind. For reasons that I don't quite understand, but here's what he said. He said, well, the principles of parameters approach open the possibility for serious investigation of the third factor. Sounds like a science fiction movie from the 1980s. And he said, and the attempt to account for properties of language in terms of general considerations of computational efficiency. Okay. And so in fact, he evidently had said, well, let's try it, right? He thinks that there might be some way of doing this. So how might we do that? I think that it's fair to say that the Chomskyan literature, either Chomsky himself or the literature in minimalist syntax, has not been supremely successful in characterizing what they mean by computational efficiency in a rigorous way that I think explains properties of grammar. But there has been, as you guys know, other ways of doing this. So Aravind Joshi introduced the mildly context-sensitive languages. And this class of languages was intended as a kind of upper bound, a kind of thing that was sufficiently rich so that we could deal with Schieber's case, but not so powerful as to open the door to anything. Okay, and so Aravind suggested that there are three properties that characterize mildly context-sensitive languages. One is you have to be able to get Swiss German, but also not too much. Okay, so remember that the not too much is less widely discussed. He sort of said not too much, but the only thing that I think he said explicitly about what he means by not too much is you should get things like WW, but probably not mix. So arbitrary groupings of, you know, arbitrary interactions of A's, B's, and C's, or of nouns and verbs without any constraint on word order whatsoever. I think he thought that should be beyond the pale. Okay. He also proposed something called the constant growth property, where if we line up the strings of our language, we shouldn't get gaps of unbounded length. That essentially the intuition is that language grows by putting bounded chunks of structure together, and we iterate. And so we can get languages where we take those chunks and chunks and chunks and chunks and add them together, but we shouldn't get languages which grow where the spaces grow as the square of some function. And finally, he said, well, polynomial parsing. We better be able, the class of grammar should be such that we should be able to efficiently process it. So this is the idea. Now, as has been pointed out, this is not a formal definition, particularly the limited crossing dependencies where we don't even know what the upper bound is exactly. But there are various instantiations, and especially if we take the idea that we should not generate mix, there are a number of instantiations that Joshi, Vijay Shankar, and Weir famously proved to be equivalent in the 80s and early 90s. So tree adjoining grammars, combinatorial categorical grammars, and linear index grammars. Crucially, not the arbitrary class of multiple context-free grammars and minimal grammars. Those are richer. Okay, they have these properties in that they are parsable, constant growth, and they do generate Swiss German, but they both, as has been recently shown, they will generate mix. Okay. So in a sense, they are sort of more powerful than we might want if we think that that Joshi's intuition was right, that is beyond what we think a natural language ought to be able to express. For this reason, these are sort of still inside the context sensitive. I think Mark Steedman has recently given these a name, the scarcely non-context free instead of mildly context sensitive. That in a sense that this is just epsilon away from context free. It's not in the realm of context sensitive. Anyway, this is the idea. Okay. So other kinds of universals of grammar that have been proposed, and these are kind of empirically motivated. Marco Kuhlmann, in his dissertation, looking at dependency grammars or notions of dependency in general, proposed something that he called well nesting, which basically said that if we've got two dependencies that come from some word, so we have word 1 and we have one dependent which consists of word 2 and 5, and another one which consists of word 3 and 4, we see that this chunk 3 and 4 is properly contained in this 2, 5, right? Whereas here we get this kind of overlapping dependency between 2 and 4 and 3 and 5. And the idea is that well nesting rules these kinds of things out. Okay. And Kuhlmann did something interestingly, which is look empirically at certain kinds of sets of text that has been tagged for dependencies. And what he finds is that actually this well nesting property, in contrast to other properties that have been proposed as constraints on what dependencies can look like, actually allows virtually all of the text. Essentially, it seems to impose an upper bound on what is a possible dependency structure. So these are, if you consider the set of well-nested dependencies in the Prague dependency tree bank and DDT, I think it was the German dependency tree bank, these are languages with a fair amount of word order freedom, and yet all, essentially, of their dependencies satisfy this well-nesting property. So it looks like that is a plausible upper bound in the kind of complexity we see. All right. Kuhlmann also talks about this notion of block degree, and this sort of has to do with how split up a given kind of dependency arc could be. And again, here he shows that essentially that all you need is block degree 2. You never get cases of block degree 3 where they're split in, a single dependency branch is split into 3 pieces. And you would see that essentially that captures everything. Okay. So interestingly, Kuhlmann shows that the well-nested dependencies of block degree at most 2 are again exactly those that will be generated by tag and CCG. So there's a kind of convergence between what dependency structures are with certain kinds of properties and those that are general by these formalisms in Joshi's promised land. And in fact, if we limit MCFGs, multiple context free grammars, to those with fan out 2 that are well nested, this has been proven to be weakly equivalent to, again, this same class of languages. So it's a very small subset of the MCFGs, but these turn out to be of the right formal complexity. All right, so this is thinking formally about properties of grammars. Well, there is some good news about this, right? The good news is that these computational properties, not only, as Kuhlmann showed, are compatible with large chunks of corpora, but it's also the case that they allow us to derive certain kinds of properties of linguistic patterns. So a couple of the properties that I put up before, subjacency in the Williams cycle, various people, including me and Tony Kroc and Erwin Joshi, showed that these can be derivable from the properties of the formal systems themselves with certain kinds of linguistic assumptions. Similarly, there are certain kinds of constraints on ordering, not quite the final over final condition, but related things having to do with ordering the noun phrase or ordering verb clusters. Steedman and Kroc and Santorini longer ago showed that these kinds of formal systems derive constraints on what counts as a possible ordering in ways that seem to match the typology. So we get this nice fit between the typology and the formal constraint. Good news. So what's the bad news? The bad news is what started, the reason why we're all here, this is a conference on grammatical inference, is the reason we were looking at constraining what the set of possible languages is because we hoped that that would help us in grammar inference. We hoped that by limiting the set of hypotheses, that would make it easier to learn. And the problem is that it doesn't. So as you guys all know, at least from the perspective of gold, this is old news. Even the lowest rung on the Chomsky hierarchy, regular languages, which are all of these things include, that doesn't constitute a language. So what's it? Now there's another path which some of you in the audience are world experts on, or have been the innovators in doing this very thing. Don't look for classes that are in a sense orthogonal to the typical classes of the Chomsky hierarchy. Don't take those classes as God's truth. Look for other classes, and maybe we can find hierarchies of classes that are in fact learnable under standard measures. And so there have been a variety of attempts to do this in the domain of phonology. Heinz and Chanley and Jardine and Rogers and others, following Dana Anglin's work and other work, have been looking for subclasses of the regular languages which are learnable. And in the case of Heinz and Chanley and Jardine, Rogers, and so on, they've been looking at applying this to the domain of phonological patterns. Okay. I don't know much about phonological patterns, so I won't say much about them, but that's one kind of work. Another kind of work is do this in the domain of syntactic patterns. So again, some of the people who are out there, Alex Clark, and Yoshinaka, and Makoto Kanazawa, they have been looking at kinds of grammars for syntactic patterns, these kind of substitutable or congruential grammars. Okay. And they've proposed certain kinds of hierarchies of classes of grammars, which they show are learnable by certain kinds of algorithms, given the presence of certain kinds of data. Okay, so that's good. Now the question is that's sort of an interesting agenda that allows us to kind of deal with this problematic case. Now, question is, how well do the resulting classes, the goal is that there's going to be this fit between formal complexity and learning, right? That if we constrain our classes to be learnable, there should be a convergence between learnability and what our languages ought to look like. So is there a convergence between considerations of learning and considerations of linguistic typology? And I think the answer is in the domain of phonology, Jeff and colleagues have shown that things look pretty promising. So hats off to you guys. So, we have the attested properties of phonological theory. And here I'm just thinking about sort of surface generalizations, not processes, but you guys have also shown that, seems to be true in transductions as well. There's kind of elegant typologies of certain subclasses, the regular languages, that strictly local things seem to characterize certain kinds of processes, strictly piecewise, other ones strictly tier-based, strictly local, others, and so on, right? So nice kind of characterizations of certain matchings between, on the one hand, phonological domains, and on the other hand, these subclasses of regular language, learnable subclasses of regular language. So hooray, okay, this is good news. Now, further, not only that's the kind of lower bound, that's the descriptive adequacy case, and the upper bound, the explanatory adequacy, is that the impossible constraints don't seem to be statable with these subclasses. So as you guys have pointed out, there are things you could imagine, like harmony between the first segment of a word and the last segment of the word. That doesn't seem to occur. Or that all words require an even number of sibilants. Also something that doesn't seem to occur. Those sometimes seem to be statable in these subclasses. So again, it looks like we're sort of capturing typology, learnability, and but with sufficient expressiveness. Good. All right, now that's phonology. As I said, I don't know much about phonology. Let's think about syntax. So let's ask about syntax. I think here the answer is it's less clear. My student, Sophie Howe, had done a bit of work on this, and I think showed, following some observations of Thomas Graf, that things are less promising. So Graf proposed, or following Joshi, I think, looked at certain kinds of properties that we think are kind of too powerful for what we think a natural language grammar should be. And so things like these non-structural properties, like modulo, that the number of occurrences of a symbol, mod n, that it should have, or 0 mod n occurrences of some symbol, or the length of something should be 0 mod n. That turns out to be an easily learnable class. It's case substitutable. Okay. Another kind of property that's learnable is this mixed language, sort of an unconstrained crossing dependency. That also, how shows, is case substitutable. Okay. Another kind of thing that Graf suggested should not be a kind of property of natural language is where we get arbitrary copying of arbitrarily complex structures. So if we have some underlying context-free grammar, context-free language L, we can't have the language that consists of copies, unboundedly many copies, or n copies of strings from L. Okay, that sort of seems like a very powerful thing indeed, to be able to copy in some unbounded way a sort of arbitrary complex structure. There certainly is copying in some limited degree, but Graf suggested, I think plausibly so, that we don't want to allow unbounded copying. And yet, what Howe was able to show is that, in fact, this language is generated by a 3-MCFG that has the 2 finite kernel property and the 1 FCP. Okay, so this is this is therefore a learnable subclass of MCFGs. All right. So what does that tell us? What it tells us then is that this is sort of like, we don't admit the upper bound. We can, learnability by itself doesn't constrain our grammars in a way to rule out kinds of grammatical properties that we might want to rule out. Okay. Now that's not to say, of course, there's always going to be cruft, and there might be other reasons these are ruled out. So I think, this kind of modulo thing, it's hard to imagine grammars that are not going to permit things of this sort, but these kinds of structural things where these kind of crossing dependencies or these unbounded copying things, these feel like very powerful things that we're not going to be able to rule out on functional reasons. And I think that it's unfortunate that they don't follow from learnability considerations, but evidently they don't. Okay. All right. So that's sure.
So, I mean, I think, so I think the idea that the typology is going to follow directly from the learnability is asking too much of the learnability, because I think there's probably lots of small learnable subclasses, but only some of them are going to correspond to the linguistically interesting ones. So I think the idea is not that any learnable subclass should be linguistically interesting. I think the idea is to find those learnable subclasses that are linguistically interesting. That's how I would think about it.
Yeah, and can I chime in too? I mean,
Absolutely.
I completely agree with this, and I think these classes there's all sorts of weird stuff you can learn. I slightly feel that this sort of weak learning is slightly too easy. And that when you focus on strong learning, on learning the syntactic structures, then it's a much more constrained space. Mm-hmm. And I have no idea whether that's going to give a result that will satisfy, linguists' ideas of what should fall out from learnability. But I think it seems like a more constrained space, even though it's much less developed at the moment. So I mean, I sometimes feel syntacticians are like only interested in movement, which is a bit of an exaggeration, but so it's kind of only when you're talking about strong learnability of mildly context-sensitive formalisms that they'll sort of even kind of start to get into that syntactically interesting territory. So that was more of
it's also going to be the case that's where those are going to be what linguists call movements, right? Those are going to be the cases where they're going to have some interesting formal complexity, right?
Exactly.
So yeah, I mean, although there's this final over final condition, I don't think we're going to be able to get that on learnability considerations. But Alex, I agree absolutely with what you say. And the fact that I'm not talking about learnability here is, I apologize, just my own ignorance of the really interesting work that you've been doing. And I, it's my own, I've got to study that work more, and or maybe I should get Sophie to study it more and to pursue this.
And it's fascinating. Please continue. Sorry, I didn't want to derail it.
No. Thank you very much. But absolutely. And Jeff, to respond to your question about other factors, absolutely. Folks will often say, folks who are kind of non-generativists will actually say, well, all of it has nothing to do with learnability. It's just it's functional considerations, or it's historical residue, or whatever, or it's the desire to be cool, and when you say certain things, people think that's cool. I'm joking, right? But I think that there, of course, are all sorts of other considerations. The question is, just as we, I think, hold ourselves to a fairly high bar, it's not enough just to say, oh, there are other considerations. The problem is making it work. And so, for example, there's an interesting thing about the well-nestedness. There was some interesting work done of does well-nestedness follow from issues of memory load? Because you could imagine it has to do with memory load. And so recently or does it follow just from the statistics of the kinds of things that people see, so that they don't, you wouldn't expect to find more than 0.05% of examples like that, just because, those kinds of things don't happen. And so actually there was some work that was done, I'm forgetting the authors, I apologize to them and to you, but where they looked at this, and they were kind of hoping that was going to be the answer. And in fact, that gave quite a different answer. It gave an answer that you would expect many more examples than. So I think we've got to be serious. And there are some attempts to do it, but I don't think that the attempts to kind of do kind of other reductionist explanations for some of these things, certainly the kind of unconstrained crossing dependencies that are like, it's not obvious how to do it. I know that you've thought about this in the domain of phonology for some cases, yeah. All right. Any other questions? Thank you. This is super interesting. All right. So now I'm actually supposed to get to what I'm supposed to talk about. Oh my God, it's already 9 o'clock. I thought I was going to have nothing to say. Here we go. So here's the world of neural networks. So as you guys know, if you've put your head in under the rock that is the world of computational linguistics, which is a rock that I had not put my head under or taken my head out from under in a long time. And I have recently started going to those meetings, and it's kind of a different world. And the different world is that, grammar's bad. Neural networks that are opaque and inexplicable, good, because gosh darn it, you can make great systems that use them. And so, as you may know, there are these different architectures for neural networks. One of the standard architectures is the so-called recurrent neural network, where you might have some input string, these x's, and you have this procedure by which you map to some set of outputs the y's. Okay, and the way that this is done is that the x's are some kind of vector. It's an input word that is mapped to a vector. That's called an embedding. And we then compute some hidden state, that's the light blue, which we'll call the a's. And this a is computed via some linear map applied to the previous hidden state and the previous and the input. And we add those, and we have some bias vector on b. And then we apply a tanh function, because why not? Bounds it between -1 and 1. And then we, again, apply another linear map to the output of that, and bias vector, and do a softmax. So we get some kind of output, some kind of probability distribution of what do we predict at this point. Okay, so that's the model, and we kind of transduce from a sequence of x's to a sequence of y's. You can also look at this kind of model as a model of acceptance, that essentially you ignore all the outputs but the last one, and you have some target thing says, give me a grammaticality judgment, and it will just say yes or no. Y hat is just a vector of length 2, and it's going to give you a probability distribution. Is it in a language? Is it not? All right, this is how recurrent networks work. This is a very simple kind of recurrent network that is called, wouldn't you know it, a simple recurrent network. This was first proposed by Jeff Ellman in the 80s, I guess early 90s. And there have been other variants of the recurrent network. One of them is called an Lstm. Lstm basically just replaces this very simple computation in the Ellman network with this more complicated computation that replaces the blue box. Don't worry about its details for now. There's another more complex version, which is called a GRU, which is somewhat less complex. If we have time, we'll get to the distinctions between LSTMs and GRUs, but that's a recurrent network. Okay. Now, these things have been made more complex in other ways. You can have a recurrent network that not only does one computation and gives an output, but it does one step of computation. Those kind of hidden vectors, or those state vectors, that's what we're essentially computing, that was used to directly compute the output, those state vectors could then be fed as inputs to a subsequent computation of another set of state vectors, and so on and so on and so on, k many times. These are what you may have heard of as deep neural networks. Deep just refers to the number of layers of computation that intervenes between the input and the output. Okay, so we say that networks are deep to the degree that they have multiple layers of representation. Another innovation in the world of neural networks that you may have heard, that's all the rage these days, is what's called attention. So right now, when we compute these even in the deep networks, when you compute the state is conditioned on the previous time step state and your current input. Even with deep networks, that's all you're conditioned by. With attention, essentially, you get access to all the time steps simultaneously. So this guy can look at here, and maybe even here, or maybe you can just constrain to look at previous time steps. So this guy can now look at it here and here. And if you have longer strings, they get lots of possible inputs. So they're not constrained as to where they can look. How do they know where to look? If you have to look everywhere, you're looking nowhere. Well, there's some process by which you assign weights to these different time steps. These are what are called the attention masks. And this is captured essentially by some comparison of representations. I will not talk about for now how exactly that's done. Okay, so that's attention. And this kind of attention thing here is just a kind of simple network or a recurrent network with attention. It turns out that attention, this network has this recurrence where you are computing a state on the basis of the previous state at a given level, and you've added attention, but people had the idea, and there was a cleverly titled paper called Attention is All You Need, where people said, okay, once we're doing this, let's just punt entirely on the recurrence. On a state being sensitive to the previous state, let's just eliminate recurrence and only use attention. So we've got some very deep network, and we will just pass information from one time step to the other using attention. So we'll get to look everywhere simultaneously. Not really what seems to be a plausible cognitive model, perhaps, but that's the idea of these attention networks. This kind of network is called a transformer, kind of this rather complex Frankenstein monster, but there it is. There's the kind of canonical picture of a transformer from one of the papers. Now, it turns out because there's no longer any kind of recurrence, there's no implicit representation of ordering. Everything is kind of presented in parallel. So what this requires is some kind of explicit representation of the position of an input. So we can't any longer just give it the input as a sequence and let it deal with it. You have to say, this is input A in position 1, input B in position 2, and so on. We've got to encode that explicitly. Okay, so that's what's called this positional encoding. Okay, we've got to get that explicitly. All right, so there's lots to this picture. I'm not going to explain it, but here's the attention mechanism and so on. Okay, good. So now let's ask the question that we were asking before about descriptive adequacy. We don't have grammars anymore, but we can at least ask, are these things sufficient? If we think about descriptive adequacy as lower bounds, are these things sufficiently powerful to capture the kind of problem patterns that we want? Well, you may know there are these classic results from Siegelman and Sontag, which showed that these recurrent neural networks actually can compute all Turing-machine computable functions. So sure, they're sufficiently powerful. And there's a recent result from Perez and Batamishra, where they show, yes, and transformers too. So and the way they show that, as you might imagine, is not by reducing a Turing machine to a transformer, but rather by reducing an RNN to a transformer, showing the transformer to simulate. Okay. Now it turns out there's a slight footnote that we should put on these sort of universality results, and the footnote is that both of these results require arbitrary precision. So the vectors that are computed here have to be arbitrary rational numbers. They don't require arbitrary real numbers, but arbitrary rational numbers. And moreover, they require, unsurprisingly, unbounded computation time, because computation can be unbounded in time. So one question is, well, that's fine, but what happens if we sort of impose some more reasonable limits? Okay. And so here's some work that actually I think you'll hear more about on Friday when Gail Weiss gives her tutorial. If you impose bounds on, say, the precision, okay, so you, in other words, what Will Merrill called saturate the values of the network, so that essentially, instead of having arbitrary values, you have essentially 0, 1, or some bounded set of values. All of a sudden, the power of at least some of the recurrent networks, the SRNs and the GRUs, converge to regular lengths. So they become quite limited indeed. LSTMs actually behave differently. They turn out to be a subset, unknown whether it's proper, of the real-time counter languages. So the distinction between LSTMs on the one hand, or at least saturated LSTMs on the one hand, and SRNs and GRUs on the other, is that LSTMs are unbounded in their activations. So they can essentially count. The mechanisms they have allow their equations that I went through very quickly before allow them to count, whereas SRNs and GRUs can't. So they can just represent ones and zeros, and LSTMs can count things. Okay, so we get essentially the calculation. It turns out if you allow yourself bounded time, but you allow yourself a little bit more precision, something like log n precision, turns out that even simple recurrent networks can represent, so this is kind of depressing, this is not much, at least for syntax. If you give yourself a little bit more precision, SRNs can represent nested and crossing dependencies, essentially encoding a stack. It's as yet unknown, what do you have to assume about precision? What do you need to assume about time complexity in order to allow mix or unbounded copying? What is the crucial thing that will push you too far, right? So what is the kind of complexity limit on what you want to give yourself what you want without giving yourself too much? And I think that's unknown. Do these things enforce constant growth and well nesting under certain conditions? We know that certainly the counter languages and the regular languages are constant growth, so that's good. But what about well nesting? Do we know, do these kinds of the things that they're able to represent, do they enforce well nesting? Don't know. Okay. Okay, so I think that's sort of open question. Now, what about transformers? Well, here too, there are some preliminary results about sort of their descriptive adequacy, the kind of lower bounds on the complexity. So Michael Hahn in a 2020 paper showed for 2 languages, he looked at parity language, so the language of strings of zeros and ones that has an even number, say, of zeros, or the Dyke2 language, essentially the sets of strings of paired brackets, 2 kinds of brackets. Kind of the idea of the Dyke languages is some sort of pure representation of hierarchical structure. What Hahn showed is that neither parity nor Dyke2 are in the languages that are representable by a hard attention transformer. Now, what do I mean by a hard attention transformer? What I told you that an attention mechanism is one that looks at other time steps and kind of takes a weighted average on the basis of these attention masks. A hard attention transformer does that. It looks at all the different time steps, but then it's required to just choose one place to look at. Okay, so it computes a kind of ranking of how interesting all of my neighbors are, and then it just picks one as its most interesting neighbor and uses that as its computation. Okay, so what Hahn shows is that these kinds of languages, these 2 languages in particular, are beyond the capacity of hard transformers. My colleagues, Dana Anglewin and Sophie Howe, have generalized Hahn's result and have shown that actually hard transformer attention are not only, don't generate parity and Dyke2, but they're actually upper bounded by AC, the class, complexity class AC0. the languages that are accepted by constant depth, polynomial size, Boolean circuits. Okay, so from that, these two things follow and more. Okay, so many other languages that are not in AC0, so majority is not in AC0, and so you get lots of things from that. Okay, and now what's interesting is there was a subsequent paper by Yao et al. A lot of work on this these days, where they show that if you consider Dyke K, so we not only have two kinds of brackets, we have K many brackets. If we only consider those strings where the amount of embedding is at of any point in the string is at most depth, D, a hard attention transformer with D+1 layers can recognize that. But this, it turns out to require order log n precision. Okay, so we can get bounded depth Dyke strings, this bounded depth hierarchy, but not unbounded depth. Okay. All right, so that's one thing that's known about hard attention. What happens if we loosen our restrictions on hard attention to allow ourselves to have the kind of general attention where we get to see everywhere and take weighted sums? Well, it turns out that now things are more powerful. Yao et al. Show in a very odd property of their paper, they show first that you can get a soft attention transformer can recognize bounded depth Dyke K. And then in the appendix of this paper, for reasons that I don't understand, maybe someone in the audience understands this more than I do, they actually have this much more general result, which is that actually a two-layer soft attention transformer can recognize Dyke K. So yes, soft attention evidently gives you much more complexity than hard attention. Okay. Dyke K might be a good thing to recognize in the sense that that's the kind of hierarchical structure we've got in natural language. So this might be an interesting model to look at. So what we should get from there is two things. One is, first of all, that Yao et al.'s construction employs not only soft attention, but also employs hard attention. So that's first observation. So they claim, they portray it as this result about, oh, it's hard attention, it's soft attention, but in fact, it's the conjunction of soft attention and hard attention that is necessary. And note two is that in order to do this construction, they also require, remember I mentioned positional encodings or positional embeddings, they require a certain sort of what I think is a kind of non-standard positional embedding, where a position is kind of a ratio of, it's a rational number, which is a ratio of the position divided by the length of the string. So if you're position I of a string of length n, the number that you get to encode position is I divided by n. So you use that, and then you can do this construction. Okay. So what do these facts point to? Well, I don't know exactly what they point to with respect to natural language, but what they do point to is a conclusion that was recently championed in a paper that Marco Baroni posted this summer, which was that, well, if we want linguists, and I think it's useful, and linguists and people interested in grammatical inference, to sort of take seriously the study of these neural network models of language, we, the computational linguistics community, need to take the details of those models much more seriously. I think that the trend in that field is really, well, you know, I'm just going to do whatever. It's very much kind of an engineering discipline where I'm just going to hack the model and modify it at will and just tweak various details. But I think what Baroni points out and what this Yao et al. Result shows us, for example, is that these details really matter. And we might change things just out of convenience, but they might have massive effects on the sort of the expressive capacity of a certain kind of network. And so if we want to really study them, we've got to fix them. And it's a difficult business because these things are changing so quickly. But I think we're only going to make progress in understanding what the properties of these models are by looking much more carefully at what are the properties that really condition their ability to express certain kinds of generalizations. Okay, so this so far has been a discussion about descriptive adequacy. So what about explanatory adequacy? So do the neural networks provide a basis for the learning of grammatical patterns? So here, I don't have that much to say, and that's good because I only have like 15 minutes left. But let me say it, what I have to say. So remember going back to Chomsky's idea. The idea was that our linguistic theory provides this kind of evaluation metric, this ranking of hypotheses. And you think about, well, what's going on? How do we even think about that? In the notion of a grammar, we can talk about simplicity, right? I can think about, I can count the number of symbols that is required in order to encode a context-free grammar or an MCFG or pick your favorite grammar formalism. But what happens when your model consists of these ginormous weight matrices of millions or billions of parameters? What counts as simplicity, or what's the inductive bias of a gradient descent learner? How do we characterize that? And in fact, there has been a certain amount of work on that. There's been some suggestion that we could look at the properties of these enormous weight matrices. So one initial hypothesis was that you could think about the norms of these matrices, that the size of these weights themselves, and that you might expect that as you are learning, there might be some pressure for those norms to shrink, okay, to kind of become sparser and to focus the weights only on the weights that matter, okay. And there was some work that had been done in a very, very simplified neural network, essentially a one-layer neural network that was designed to do matrix factorization, and where that was found. But then in subsequent work that looked at a kind of more general class and the theoretical context, this is this paper by Raisin and Cohen, they showed that in fact, this is not true even in the domain of matrix factorization. In fact, what they showed was that, they showed that in fact, as we look at learning in these networks, as they tend towards convergence, in successful convergence in this task of matrix factorization, their norms are not being minimized. And they make a suggestion that maybe we should look at matrix rank. They don't really explore that extensively, but that seems like another possibility. But what they do find is, in fact, what we see is that the norms are not only not shrinking, they are growing systematically, that the norms are tending towards infinity, okay? And so as you are converging, norms are growing, okay? So you might say, well, that sort of just means, well, there are two possibilities. One, I think, which was Raisin and Cohen's conclusion, which was, this is the wrong thing to be looking at. The other possibility is, this isn't the wrong thing to be looking at, but rather maybe the growth in the norm is telling us something about the prior or about the inductive bias of these networks. So we can ask, what is the effect of norm growth on the computational capacity of the network? And so what is it tending towards? And there's some interesting recent work by my former student, Will Merrill, where he actually made this observation about norm growth, which is essentially if the weights are increasing in size, and we've got these activation functions, functions that are leading to the computation of the different units of these sort, like tan H or sigmoid, what that's going to tend towards is a model that is saturated, where we're in the part of the function where essentially we're flat. Okay, so essentially the activations are going to be either 1 or -1 or 1 and 0, depending on your activation function. Okay, so these are going to be analogous to like the hard attention models. Okay, so we have either saturated models where everything's sort of, they're not arbitrary real values. We just have a bounded amount of precision, 1s and 0s, or the attention is only looking at one place. And these are, in fact, as we noted above, both in the context of both saturated, these bounded precision models or hard attention models, these are associated with weak expressivity. Okay, we saw that both in the case of the transformer and in the case of the recurrent neural network. So we saw, for example, that LSTMs are not actually equal. They're a subset of the counter languages. And so what Shibata et al. Found empirically was that if you look at LSTM language models, empirically, they found out, in fact, this is true. It's not just a fact of theory. It's true in theory, but what about in practice? Well, in fact, yes, they look at the particular activations of these different things, and they find that, yes, even though they could be a kind of continuous mush between -1 and 1 or between 1 and 0, in fact, we get essentially bimodal distributions or distributions at 1, 0, and -1. Okay, so this is what happens in the wild when you train these networks on the Penn tree bank. You get networks that essentially are doing this kind of norm growth, leading to saturation. And we see this as well. Merrill et al. found this argued for this not only theoretically, but found that you get norm growth when you look at the training of these very, very large transformer models. So this is a model that has been, one of the kind of currently popular models, T5. And what they found was that norm growth increases over training, varies somewhat how much it grows over time with the different layers. It seems to grow more in the upper layers than in the lower layers. But this is the picture. They also show theoretically that it ought to grow as a square root. And they get a pretty good fit with what we actually see and this kind of square root rate of growth. So that's exciting. And in fact, if you look at, they sort of compared the activations of the pre-trained networks with saturated versions, where essentially you multiply all of these activations by some large constant, I think it was 1,000, and then you take the correlations with the outputs in one case and the outputs in the other, you get high correlations for the pre-trained networks and not very good for the untrained networks. Okay. So in other words, what it looks like we're getting is that for these large transformers, we're getting, especially for the upper layers, we're getting performance that looks like it is tending towards saturation, that there seems to be a kind of inductive bias in favor of saturation. Now, I think that's good, because it means that we might have the beginnings of an understanding of what is the inductive bias of these networks. It's bad in the sense that our previous the complexity riddles tell us that those models are not very powerful indeed. So what it suggests is we might need to look at other kinds of models where saturation, say, if that's an inevitable consequence of gradient descent, won't have the same kind of detrimental effect. Okay, now what I was going to talk about, if I had a little more time, not 7 minutes, was whether the learning trajectories we find in networks actually favor grammatical generalization. So this is the kind of second part. Do the things not only limit the complexity, but do they give us the right kind of generalization? Do they favor a structural generalization as opposed to a linear generalization? But given time, maybe I will stop here. And the short answer is that they do not. So at least in the domain of recurrent neural networks, and somewhat, and to the degree that we've looked at it in the domain of transformers as well, these networks, when faced with ambiguous data that is analyzable either in terms of kind of structural properties or linear properties, they seem to have a bias in favor of the linear generalizations, particularly so for LSTMs, where they seem to have this capacity and preference to count, that they really do prefer linear generalizations. And so as yet, the only way we've found that we can bias networks in favor of structural generalizations is essentially to build structure into the networks, to give them, to say that what we want you to do is decode a syntactic structure whose properties we are going to give you. That, in fact, that is sufficient to bias the network to favor structural generalization. But short of that, we have not found any kind of general architectural considerations which lead to structure as opposed to linear bias. And this is, I think, still a wide open question. There's a lot of work now, I think, in this area where people are looking at, well, how can we augment the data set in a way that will lead to structural generalization? So a lot of work on compositionality and how can we get networks, they often will behave in a way that works well for a certain set of examples. And if you look at another set of examples that seems to just involve some kind of reshuffling of the units on which it's been trained, they fail dramatically. They don't seem to show compositional behavior. And so one response in the NLP community has been, well, all that we need to do is augment our data set. And so what I'm going to do is take my data set and introduce more compositionality into the data set. And sure, it's the case that the network will then behave better. It will behave in a more compositional fashion. But in a sense, that's not really addressing the puzzle of when the data is sparse, as it inevitably will be. It's a bit of a game of whack-a-mole. What is the preference for the network? What is the way in which it will generalize? And I think this way of just trying to solve the problem by data augmentation seems to me to be barking up the wrong tree. So I think this question of what are the architectural refinements that we need is still wide open. And I think that People from the grammatical inference community, I think, have a lot of experience about thinking about different kinds of models and thinking about different ways of evaluating the strengths and weaknesses of that models. And so it will be exciting for you all to engage with this community. So let me thank you, and I hope this was comprehensible and useful. All right. I see a bunch of hands. Thank you. All right, Dakota, I think that you have your hand up.
I do. Sorry if the AC is blaring very loudly into my microphone.
Well, Zoom has lovely noise. Well, sometimes lovely, sometimes less lovely, but it seems to be killing the high frequency.
Oh, excellent. So I feel like you addressed this and I probably just missed it. But so if learning is supposed to take into account structural biases in the language, how is this approach supposed to account for things like the fact that Swiss German does exist with its non-nested dependencies, or people like me exist who don't have island constraints?
So are you suggesting that those things are suggestive of lack of structure?
I'm not suggesting that they're suggestive of lack of structure. I'm just like, if the structure that we're trying to account for isn't a structure that allows for these things, because that seems to be the general approach, is saying, okay, well, most of the time we have not this, so let's avoid this.
Well, I definitely do not believe that. I mean, I am happy to believe that you exist, even if on your screen you look a little bit like a cat. But I have seen you before, and I know you exist, and so I know that, and I believe that your grammar exists, and so I think that it is the responsibility of our theory to characterize that. And so I don't. Maybe it's just a kind of misunderstanding. It's not sufficient to just say, oh, we should get 95% and the rest of the 5%, to heck with it. No. And so I guess I'm not understanding exactly when I say structural bias, I do mean a structure that is sufficiently rich. I don't mean, by structure, I don't mean simply context free. I mean, whatever kind of structure is necessary to characterize the grammars that we observe, including yours.
I think that's fair. I think my question just stems from, like, oftentimes I'll attend these sorts of conferences and hear people talk about constraints that specifically rule out things that, I allow, or that speakers of other languages allow. And I'm like, this constraint feels wrong.
Well, then the constraint is wrong, right? Then I mean, we always need to analyze these things, right? A single unanalyzed data point, one needs to kind of be careful with it. But we need to take these data seriously and understand them and see what the basis is. And so we've got things like there's a whole lot of Norwegian speakers who apparently do not abide by certain kinds of island constraints. And there's some interesting experimental work. Dave Cush and others have been looking at whether it's really true, as has been claimed by Engdahl for some years, that the Norwegians don't abide by island constraints. And I think Dave went in thinking that no, they do, silly. It's just you're just you're barking up the wrong tree. But in fact, I think he thinks no. In fact, we need to better understand what the landscape is, and if the claimed objective is wrong, we got. I mean, but that's just sort of the usual state of affairs of linguistics, right?
Yeah, that's fair. Thank you.
Thanks. I thought I saw a couple of other hands. Let me see. Now I can't see them.
I think we were just clapping for you at that point.
Okay. Alex.
Hi, yeah, thanks for a really fascinating talk. I've got lots of questions, but I was just kind of talking about the final part of your talk where you're trying to think about the sort of inductive biases of these deep neural network models, which is kind of a very kind of dynamic topic at the moment.
Yeah.
And I was just thinking about whether, I mean, one way in which the success of these models has kind of changed my view about learning in general is that it used to be kind of a kind of, particularly among linguists, article of faith that in order to learn, you need to have a very restricted hypothesis space, right?
Well, not the original Chomsky, but the later Chomsky, yes.
Yeah, so, but I mean, one of the ways in which, and that's kind of, you know, from a sort of traditional machine learning theory perspective, you know, VC dimension, all that, you're kind of taught, you know, that you need to control the capacity of your learn in order to guarantee generalization. But then these deep neural networks come along, which are like massively overparameterized and kind of Turing complete, and you know, basically essentially have unbounded capacity. And so that's sort of, I'm still in the process of sort of kind of trying to erase the bits of my brain that have wrong intuitions about this. But I was kind of thinking you seem to be slightly more advanced in this process. And I was just wondering if you kind of, how do you sort of reconcile these? I mean, is it just that the traditional linguistic view is sort of incorrect, or is it that there's the way in which these deep learning models is deployed is just like not really relevant to the problem of language acquisition because they got lots more data and they're trained for multiple epochs and so on.
Well, I think
it's a kind of vague question, but
yeah, it's a great question. I think it's the question, and I think that if I conveyed the idea that I understand this any better than you, I think I pulled one over on you. But no, I think that one way in which, with respect to what you said, I think I'm not so sure that, well, for sure, the capacity of these networks is vast, is true, right? They are massively over parameterized, but I think we're still not sure exactly what their capacity is. What is learnable in a kind of gradient descent kind of paradigm. And so this is where these results of Merrill and others about the sort of norm increase are, I think, very, very telling, because it says that, well, what's going to happen in learning is that, in fact, the capacity that they have in principle, there are all sorts of things that they could be doing, but they're not going to do that in the end. So are not going to be, you know, are not going to be realized. And so I think that's why it's all the more important that we understand what is going to be, what are we going to be tending towards, and what's there, what's at the end of the road. But with respect to what they tell us about, you know, how we ought to think about the kind of language learning, I'm not, the puzzle I have, I am impressed, and maybe this isn't the question you're asking, but let me take the time-worn strategy of just answering another question, which is, I am very impressed by what these models have been able to do. I mean, it's nothing short of remarkable. That said, from the perspective of the problems that we're interested in, of the problem of inducing sort of some general representation of a language from a finite set of data, it's not at all clear how well these models are doing. And I think that, let me say a little bit more specifically why I think that. I think that the paradigm has been just give them as much data as possible and then test on some data. And it's always in sample data. And we don't really understand to what degree these things are actually generalizing and to what degree they're not. There have been some very narrow studies of the nature of generalization. Do we get generalization to novel strings of, you know, words in the same grammatical category? But really, if we get grammatical generalization of the sort that I know that you care about, and I certainly care about, we don't know because we don't know very much about the nature of the data on which these models are trained. And so the degree to which they're able to, are they just memorizing or are they really abstracting in some meaningful way? I don't know. And it's the difficult thing in the community has been that I think there's not a huge amount of interest. I think much of the community is really devoted towards, let's just grow the data sets and make our models perform better on some task. Do you have a sense, Alex, about, is there anything that convinces you that you should rethink this and that there are demonstrations where you've seen these models succeed in ways that you wouldn't have expected? I'm thinking about, for example, Alex, you earlier in your career, you did these models of automata learning, right? And you won some competitions that, so what happens if you take a deep network and try to get it to do that? Do we know how well they will do?
Yeah, so I mean, Chihiro Shibata, who's kind of lurking somewhere here, has done some work showing that these kind of deep learning networks are quite successful at learning some of these automated type things. So I think it can be. I mean, I'm kind of yeah, I'm sort of fascinated by, as everybody is, by the success of these deep neural networks, and I'm kind of interested in the extent to which you need sort of explicit structural biases, like with using external data structures, or whether the implicit biases of things like transformers are going to be enough.
I don't know of any cases where, I mean, the trend certainly has been away from them.
Yeah. So you just have it baked in. I mean, one other question, which I kind of, I mean, if there are any other hands, I'll give way to them, but if not, I'll
actually, we're running into our break time. We have a very brief
okay.
break, so I think we're going to have to cut this off.
Okay.
But you can keep it going in the chat, maybe.
Sure.
Okay, thank you.
Thanks so much.
Thank you, Bob. Okay, so let's take a 2-minute